Okay, welcome everybody to another Math Climate Research Network Colloquium. Today we're lucky to be hearing from Dr. Seth Cowall, who is a professor at the University of Georgia. His research areas are in mathematical biology, dynamical systems, and environmental mathematics, and particularly mathematics and climate. And today he will be talking to us about data-driven dynamics of phytoplankton blooms in reaction-diffusion NPZ models. So with that, please take it away.
Okay, all right. Thank you everyone for coming. And just in case you didn't hear the discussion before before my introduction, and thank you for the introduction, by the way. The one thing I'm looking at right now is my slides. I'm having trouble getting the slides to work and looking at the Google Meeting at the same time. I'm used to Zoom. So if you have a question, please unmute your microphone and speak up, because that's about the only way I'm gonna know. So all right. So with that being said, I'm just gonna use my my mouse. Can everybody see that? Just someone say yes.
Yep.
Okay, great. Okay. So anyway, this is joint work between myself and Pam Cook of the math department at the University of Delaware, and also Matthew Oliver, a biological oceanographer, also at the University of Delaware. And in this talk, first we're going to talk about why phytoplankton are important, what we mean by a bloom, and why those are important, and the underlying causes for them. And we're going to attempt to simulate a bloom first by constructing an ordinary differential equation model known as an NPZ model. I'll explain more about that later. And then to add a little bit more realism to the model, we'll add a depth variable, and we'll end up with a reaction-diffusion model. And then we'll talk about what inferences we can talk about from our results, and hopefully we'll have a more ecological explanation for a marine plankton bloom. We're going to focus our efforts in the middle of the ocean or larger body of water, like say like a Mediterranean Sea, Black Sea, something like that. Not coastal or inland algal blooms. Okay, so phytoplankton. Why are they important? Well, first, they're the base of the marine food web, which is very important for fisheries. They're also responsible for much of the oxygen in the atmosphere, and I'm just going to leave it as much because estimates vary based on the literature. There's a saying that, let's see, every other breath we take, thank the phytoplankton. A lot of people are aware that that a lot of the oxygen we breathe is from terrestrial plants, but the other half is from marine phytoplankton, and they're also a sink of atmospheric carbon dioxide. Now, being at the bottom of the food chain in the ocean, most of them for death means being eaten by something, but for the lucky ones, about 1% of them, when they die, they sink to the bottom of the ocean, and they take atmospheric carbon dioxide with them. And this is known as the biological pump. And understanding seasonal blooms, by bloom I mean a rapid increase in the phytoplankton population. This helps quantify the strength of the biological pump, and thus makes it very important for makes them very important for atmospheric sciences. Okay, now you might be wondering, well, why are how does a microscopic organism have such a large influence over the atmosphere? Well, hopefully these two pictures will these photographs taken from space will give you a better perspective on this. On the left is the Black Sea during the coccolithophore bloom. All this fluorescent blue you see in the water here, that's all coccolithophores, which is one of many species of phytoplankton. And on the left is Ireland. I had to typeset Ireland for for those of you who are like me, don't recognize the exact shape of that. Of course, we panned out. I recognize it, and of course, right here at this the off the southwestern coast is a nice large bloom with an eddy in the middle of it. So actually, you can find a lot more spectacular images like this. If you go to just for fun, go to Google Images and just keywords plankton blooms seen from space, and you'll see lots of images like this. So yes, these things exist in such large numbers that yes, they do have quite an influence in the composition, in the chemical composition of our atmosphere. Okay, with that being said, a lot of these blooms happen to be seasonal, and in particular, the North Atlantic. Every year there's a bloom in the spring, and the underlying cause of phytoplankton blooms has been a debate amongst oceanographers for decades. And a lot of the original theories of what causes the blooms naturally would suggest that, well, since they're seasonal, then perhaps seasonal changes in environmental conditions are what's affecting the phytoplankton physiology directly. Things such as, well, changes in solar radiation. Sun's more intense in the summer than it is in the winter, especially, well, at least in the high latitudes. Changes in turbulent diffusivity, seasonal changes in mixed layer depth. And for those of you who are not familiar with that, I will talk more in depth about that later. But a lot of studies in the past have suggested that these seasonal changes affected the phytoplankton, their biology directly. But a paradigm shift was proposed by Barenfeld and Boss in 2014, which suggested that these seasonal forcings instead they disrupt the balance of the predator-prey relationship between the phytoplankton and their immediate predators, zooplankton, also pronounced zooplankton if you like. Okay, so let's see what we can find. Let's see what we can learn by building a mathematical model, and we'll start with ODEs. Let's see. Okay, so here is where we're all introduced to you. If you never, in case you haven't heard of these before, an NPZ model. All right, NPZ model is a system of three coupled differential equations with a state variable for nutrients, one for phytoplankton and one for zooplankton. And this, there are a great many different versions of NPZ models. This happens to be a one that's very widely studied and cited from Franks, Rubowski, and Fleer from 1986, with the exception of one modification that we made, and that is this parameter rho right here. Rho is the phytoplankton response to sunlight, capital I, and we'll just say I for irradiance. But other than that, it's the same thing as their model. So let's just quick go through the mechanics of this. Phytoplankton, they are photosynthesizers. So like terrestrial plants, they need sunlight and they need nutrients to grow. And in this growth term right here is all in green. And let's see, this parameter rho is an increasing function of solar radiation, and it's what the range of the functions between 0 and 1. And as n gets large, this nutrient function will saturate to 1. So when we have maximum sunlight and maximum and very high nutrients, then what we have is this limiting growth rate. We'll call this mu max. Okay, so notice this growth rate is in the phytoplankton equation. it also shows up as a negative in the nutrient equation because the nutrients loss is the phytoplankton gain. And over here in red, we have the predation term. And that's just as the zooplankton graze on phytoplankton. And of course, it's a negative in the phytoplankton equation and a positive in the zooplankton equation because the phytoplankton's loss is the zooplankton's gain. And for both types of plankton, we have linear death terms or mortalities, as I chose M for both of them, or M sub P and M sub Z. But dead plankton can, when they decompose, they go through a process called remineralization, where they become suitable for phytoplankton to consume again, and some of them can be recycled back into the system as nutrients. For those that don't sink to the bottom of the ocean. So in this particular model, we'll make a simplifying assumption that we have a closed system and all the plankton gets recycled. And with that convenient simplification, we end up with a closed system. This would mean that the sum of our state variables would be equal to a constant. And let's see, anything else I want to say before I move on? Okay. All right. Any questions so far? All right.
I have a question.
Sure, go ahead.
How do you define row subi?
Row subi, you said?
Yeah.
Oh, I will address that later.
Okay.
Okay. All right. There was one other thing that's just on my mind. Oh yeah. Technically speaking, the units for all three state variables is millimoles of nitrogen per meter cubed. So we're just using the limiting nutrient as nitrogen. And this is technically nitrogen that's in phytoplankton. This is nitrogen in zooplankton. But for convenience sake, I'll just continue to say phytoplankton and zooplankton rather than say that long expression over and over again. Okay, so like I said, this model has been cited often, and I seem to be frozen here. Hold on. This is strange. Okay. Okay, now I'm unfrozen. Good. Okay, so Busenberg and colleagues in their 1990 paper studied the Frank's model. Again, just imagine this row would just be would just not be there. I'll just imagine that it's one. And they did a dynamical analysis on it. They found three equilibria. One would be a plankton-free equilibrium, or if we want to call it an extinction state where there's no phytoplankton, no zooplankton. A phytoplankton-only equilibrium where we have the phytoplankton get the ocean to themselves, a positive constant for phytoplankton and no zooplankton, and a coexisting equilibrium. We consider this a balanced ecosystem where we have positive constants for phytoplankton and zooplankton. Now, we don't expect at any time for the ocean to exhibit, to look like either of the first two states. But, however, they do play some importance that we'll get to later. In particularly, the second one, the phytoplankton-only equilibrium. Another important result from Busenberg and colleagues was that when the parameters are in the range such that the coexisting equilibrium exists, the phytoplankton-only equilibrium happens to be a saddle point where the horizontal axis is the stable manifold. And just to make sure we can visualize that in the phase plane, where we have vertical axis zooplankton, horizontal axis phytoplankton, and we're not going to bother with negative axis on either one because those aren't. This is ecology. We don't. Let's see. We have our coexisting state in red here, where we have positive constants for both. We have nodes. We have the P bar, which is the equilibrium where no zooplankton, but positive constants for phytoplankton. This happens to be the saddle point, and as said before, stable manifold is the horizontal axis. Unstable manifold is going to look like a diagonal line, just like that. This happens to be an illustration, but you'll see examples later on where the unstable manifold will be a diagonal line. So anyway, so that's a little visual of what that result means. Okay. Okay. So I believe that was Emmanuel just asked me about the row. So first, so sorry to disappoint you, Emmanuel, but here's first we're going to go with a little bit of a artificial data, like a kind of a fake row. But we'll see. Once we get to the reaction-diffusion system, that's where we're going to get the full and complete version. But here, just for demonstration purposes with the ODEs, we'll just set rho to be equal to this sinusoidal function with a period of 360 days. And I just chose 360 just to make the mental arithmetic nice and easy. I know a year is actually 365 days, but the idea is with, we'll just consider day 0 to be a summer solstice, day 180 to be a winter solstice, the following winter solstice, and day 360 to be the next summer solstice, just to make this nice and easy. And remember, rho is oh, I should mention, rho is dimensionless. It is an increasing it's increasing with solar radiation, and it is a growth response to solar radiation. So as solar radiation is decreasing, okay, well, rho also decreases, and thus we have less photosynthesis going on. Naturally the phytoplankton population decreases, and there's less food for the zooplankton. But as the sunlight increases again after the winter solstice, the phytoplankton get a chance to grow without much grazing pressure, at least at first, from the zooplankton, and thus we get a rapid increase or a bloom of phytoplankton. But eventually, the zooplankton makes makes a recovery and then bounces out the system again. Now, of course, this is a conceptual model, assuming that the sunlight is the only thing, the only forcing on the system. But we'll add some more stuff later. Okay, so. All right, so this slide I don't like to use if I'm using a computer where I can make a video work. And can everyone see my screen with the faceplane day 10 at the top?
Yes.
Sweet. Okay, great. What we have here is the time series graph that I just showed you. I'm going to show you that in I'll call this an animated face plane, where at the top here row that's going to change. It's starting near 1, and phytoplankton the horizontal axis, zooplankton the vertical axis. We've got our saddle point phytoplankton only equilibrium down at the lower right, and our balanced coexisting equilibrium right here is this red X, and you'll see that you can't see it now, but the trajectory is going to be the blue line. And let's see, if as rho changes, we'll just play this video. Okay, this the system is being knocked out of balance, and as the zooplankton go down, the system, the trajectory moves towards the saddle point. But as the zooplankton make their comeback, the system moves back towards the bound state. So it seems like our bloom is more of just a just kind of a temporary push towards the phytoplankton only equilibrium. So I guess you could say the phytoplankton think they're going to get the ocean to themselves, but not quite. All right. So, okay. So that's the story with the ODEs and just having the forcing from the sun, and using we get more realistic results when we use more inputs of different types. So next thing we're going to do is we are going to add a spatial variable, and we'll just add depth. And so we have two variables now, our time and depth in the ocean. And let's see, and we're going to add in eventually we're going to add in let's see, two sources of data. One is solar radiation, just like before. We're also going to add in mixed layer depth, which is this n. And let's see, I'll just do things one at a time here. All right, first, what we're looking at is I guess an augmented version of the model we saw earlier, and I forgot to mention, I always do this. Being this is a closed system, we could rewrite n as just nt minus p minus z, and just write these two equate, and just write the p and the z equation. So that's what we're doing here. Okay, so with rho, one of the things we're doing is we're taking into account the fact that sunlight attenuates with depth in the water. So here we're adding a decaying exponential. And Kw is the light attenuation constant. And let's see, we can illustrate with this graph here with the vertical axis being depth in the water, and this top horizontal axis would be with the light intensity as a function of depth. So at the surface, we have units of Einsteins per meter squared per depth, but it'll decay exponentially, and looks like about 100 meters or so. It's essentially no photosynthesis would take place. Okay, the other augmentation we have done here is we have added diffusion terms. And our diffusion coefficient is this function right here, and this is a very simplified version of something that that we found in a paper from Gibson. It's all I really needed to do is to divide the ocean into an upper mixed layer and a lower and a calmer lower ocean, and have the thickness of that mixed layer change in time. So here earlier I mentioned that I would talk a little bit more about what mixed layer depth means. So think of the ocean in basically two layers. The upper ocean, which is the much thinner layer, relatively speaking, that would be that'd be the part that's subject to wind and waves and storms, Langmuir circulation, and let's see, what's another important one? The thermal convection. There's a lot that part of the ocean is subject to a lot of mixing, but the lower ocean is not subject to that. That's relatively calm. But keep in mind in the winter, we actually have a thermal convection and more storms and such. So as summer turns to fall, which turns into winter, you could say the mixed layer depth, the mixed layer gets thicker, or equivalently, the mixed layer depth gets deeper, M. So this would shift as the season gets colder. It would shift down, and then as winter turns to spring, turns to summer, the mixed layer gets thinner, or equivalently, the mixed layer depth gets shallower, and then this M would shift up. So this would that's what I need this function to do. And of course, and D max would be the diffusion in the mixed layer. D min would be the diffusion in the lower ocean. And we're just using diffusion as a proxy for turbulent mixing. Physically speaking, not really the same thing. It's not really the same thing, but the end result is the same. Things get spread out. Okay, so that's how we augmented our original model. And Emmanuel, here is rho in its true form is what we're using in the model, where with gamma is something called initial photosynthetic slope, and everything else is stuff we've seen in the model. So that okay. Does that answer your question?
We're still here.
Oh, okay, good. All right. Sorry about that. All right. Okay, so let's see. What else can? Okay. All right. I should also mention that when we plug in when we insert data into our model, this is data that's going to be averaged over large swaths of the ocean. That's and the data is going to be obtained from satellites. So we can definitely do that with solar radiation, and we can definitely do that with mixed layer depth. That's something that's satellites. They pick up things like let's see, like salinity and density, and they run that through an algorithm, and they estimate the mixed layer depth. It's something. Now the actual diffusive turbulence in the ocean, that's hard to measure. About the only way you can do it is in situ. And so you're gonna have to take this right here with a big grain of salt. It's very similar to what the Kuhn, Fennell, and Minturn paper does, and I can't say I blame them, because I mean, what are you going to do? You can't get that from satellites. Okay, so depth for our model, we're just setting the depth of the water column to be 350 meters, because I mean, real ocean is much deeper than that, but there's essentially no photosynthesis below there anyway. We'll just set no flux boundary conditions at the surface and at the bottom, and we'll solve this system with the Crank-Nicholson scheme. Okay, so with the ODEs, we were able to do a dynamical analysis of it. We can do that with the PDEs as well. So what we're going to do is just temporarily, we're going to hold I, D max, and M, a constant in time, and linearize the reaction diffusion model. And so so this is just the model that you've seen in the previous slide, except we're holding these three quantities constant, and we're going to use two tricks from papers from Edwards. Now, the first trick is to set up a Jacobian for our system. And let me just say, I've worked in other ecology models, and I've since found a more straightforward way to do this. but I'll just say this method also works, and the code's already written. So so I'll just go through what I did here. So just let suppose we have an equilibrium. We'll call it P tilde Z tilde. Now, the equilibrium of the reaction-diffusion system, this would be an equation of depth, but not time. So just so it's not like ODEs, where it's just a set of constants. This is just a set of functions that are not time dependent. And let P prime, let's just set that equal to, say, a P hat, a function of depth times e to the lambda t. Let's let that be a perturbation of the equilibrium, such that we have P prime equals P minus P tilde. And so many of you have probably been through this process when you linearize a system of nonlinear ODEs. So this is similar. This is similar. So we abbreviate the system. The time derivative of P equals the diffusion term plus whatever's left, which is an algebraic function of P and Z, and the other equation is pretty much the same thing, except it's the equation for zooplankton. And when we do this, we can write the following. We take the time derivative of P. Let's see, put that on the other side. We get time derivative of this would just be lambda times P hat e to the lambda t, and we get this just from the equation, and we get this line just from substitution. From the previous slide, P is just going to be P tilde plus P prime, and then we do a Taylor expansion. And then once we do that, we just do with some algebra and rearranging terms. Part of this equation just becomes the left-hand side of the equation with the equilibrium plugged in, so that part will vanish. And then what's left is this part here in the black. And if you write out the long version of that, let's see, each of these terms will either lambda t multiplied by it, so we can factor that out from both sides of the equation, and then we get this equation. And similarly, going through this same process with the zooplankton equation, we get this, and we can write these two a couple equations together in a matrix equation, and this becomes an eigenvalue problem. And with this being a Jacobian, and then what we need to do, define, assuming we have an equilibrium, which I'll explain how I compute in a minute. What we do is just take the eigenvalues of this matrix and go through them and check all the real parts. If the largest real part is negative, that means all the real parts are negative, and thus we have a stable equilibrium. But if even one of them has a positive real part, then we have an unstable equilibrium. So that tells us something. And okay, so once we do that, okay, here's actually how we get the equilibrium. First, we calculate the equilibrium for the non-diffusive system at each depth, as if each depth is its own dynamical system. Hard to put that descriptively into words, but here's what I mean by that. Take these two equations and turn them into ODEs by getting rid of the diffusion terms, and then referring to the depth variable as just as a constant. And this is, once that is discretized, we start with the surface with xi equals 0, and then just solve for the two constant ODEs, and then xi equals 0 plus delta xi, and then xi equals 0 plus 2 times delta xi, and so forth. And then we end up with a vector of ODE equilibria. And once we have that, that becomes it's pretty crude for an estimate for the equilibrium for the reaction-diffusion system, but it's good enough as I should say it's usually good enough as an initial guess for a nonlinear equation solver. And we use fsolve to solve the system, which is the system that you've seen on the screen recently, except these two were the time derivatives. Lucky enough with these, I don't think I've ever had a conversion issue, but I've had other ecology models where it does, and there are ways to get around it. You can ask me more about that later. Okay, so once we've done that, we can solve for equilibrium, and we can tell whether or not it's positive. Oh, it's positive. Excuse me. Whether or not it's stable or unstable, and that gives us quite a bit of information. Let's see. Like with the ODEs, we'd want to know. Let's see. We could run through we could take the rho parameter and find, which is just, think of that as light, turn it down low enough, and then that would give us no plankton could survive, but if we turn that up a little, but we turn that up a little more, we might have enough light to sustain just the phytoplankton. Turn it up even more, we might have enough to sustain the zooplankton population. But here, now that we have, let's just say we can vary light response, and we can also vary, let's say, Dmax, which is the diffusion in the mixed layer, and this. So let's see. So if now we can turn two knobs, diffusion and light, and see what that has on the stability properties of our three equilibria of our system. Okay, so here, and what we're going to do is, other than these two parameters, we're going to hold all other parameters constant in this grid, and say, suppose we have high diffusion and low light. That's not a good survival. That's not good conditions for survival of phytoplankton. Not only do they need to be near the surface to get sunlight, they also need to stay there, and it's hard to do. It's hard to do with a lot of turbulence in the water, constantly pulling them down and let them come back up, pulling them down again. So up here, where we have low light and high diffusion, let's see, we have the white region where the plankton-free equilibrium is stable. But if we turn up the light and turn the diffusion down, we could get into somewhere into this aqua region where we have the phytoplankton only equilibrium is stable. We have conditions that can sustain a phytoplankton population, but not enough for the zooplankton. But if we make the conditions more ideal for the phytoplankton, get somewhere into this range, then we can have a coexisting equilibrium that both exists and is stable. Okay. Any questions about this diagram? Okay, so like I said, the equilibrium of the system, there'd be functions of depth but not time. So let's do a quick illustration of a bloom in a reaction-diffusion system, and then we'll then we'll see some results when we plug in some real data. But first, I just want to show you the mechanics. All right, so first, let's let's look at this system on the left where we set rho equal to 0.35, which is pretty low. And on the right, we have a system where we set rho equals 1, that's like turn the sunlight all the way up to maximum. What we're going to do is we're going to use this system with a low sunlight as initial conditions for the system with rho equals 1. So what will happen is we expect the system to start from here on the state on the left and evolve into the state on the right. Now notice on the left we have pretty low zooplankton populations. So that ought to give the phytoplankton a chance to grow at first, and of course it does. We have initially a bloom, but the zooplankton make a recovery, and then the system settles into a balance. Okay, and I'm going to go ahead and show another animation. All right, so I'm going to show you here. That is what I showed you earlier was an animated phase plane. This is going to be an animated depth profile. Let me explain what's going on here before I run it. Okay, so this dashed curve right here, that is the coexisting equal. This is where that would be the dashed curve of the phytoplankton in a coexisting state. So if the phytoplankton had to share the ocean with the zooplankton, then they would occupy this dashed curve. Now this on further to the right is this dash dot curve. That's the phytoplankton curve if they had the ocean to themselves, or the phytoplankton only equilibrium. The only thing that's going to move in this animation is this green curve, which is going to be the time and depth dependent actual phytoplankton depth profile. So in the time series plot I showed you, that is the green curve. This is going to be its representation in this animation. Now remember, in the ODEs, the phytoplankton only equilibrium acted like a saddle point. It attracted the solution at first, and then the solution drifted away from it and settled back into the coexisting state. So that kind of happens all at once pretty quick here. So first it heads towards phytoplankton only equilibrium and then settles back into the coexisting state, and thus the system then we're back into a post-bloom balance. Okay, and as usual, these are just backup slides just in case I'm on some computer and a projector that doesn't like my animations. So we'll go ahead and skip past these. Okay, time at long last for some real data. All right, so here is some data that we acquired from satellites. This first one is solar radiation. More specifically, they call it PAR for photosynthetically active radiation. The raw data is the somewhat jagged. That's on my screen. That's like a reddish orange, and we're using to plug into our model. We're using a best fit sinusoidal curve, so that the black dash curve is what we're going to use to plug in. Otherwise, we're just getting completely noisy results. And the other part, other thing we're going to plug in is, mixed layer depth. Forgot to mention, both of these are averaged over a swath in the ocean in the North Atlantic from 40 to 45 degrees north and 20 to 25 degrees west. Think of the North Atlantic, that's about halfway between Maine and Spain. So that's a good way for me to remember it. This was a sinusoidal best fit. This was the 44th degree polynomial best fit. Okay, so how we, this is a conceptual model, but we decided just to see, just to test the performance of what we've actually put together so far. And let's see, there are two vertical axes on this third plot right here. This is for the orange part on the left here. That is for chlorophyll. That is a satellite measurement. That's in units of milligrams per meter cubed. And on the right, for our blue curve, that's our model phytoplankton in millimoles of nitrogen per meter cubed. So I should just point out right away, these are not the same units. So don't think of this as compare this as height of the graph versus height of the blue curve versus height of the orange curve, because that's not a fair comparison. But what we do have is overall structure of a bloom, and then a bounce, then a bloom and a bounce. Although we are noticeably out of phase, which is not the best. But I should mention that, let's see, I mentioned the Kuhn-Fennel and Matern paper before, that we took the construction of our rho parameter for the reaction-diffusion system. Let's see, they did an NPZD model, and they studied this same area, and they had more data inputs. They also had sea surface temperature, and they had nutrient upwelling. So they did not have a closed system. They also had a parameter optimization scheme. They had very good fits between their models, their model and their data. But what they don't have is the dynamical explanation that our study had. So it seems that our study is useful for informing the more complicated models. And I include this last graph just to make another point. In both our paper and the Kuhn-Fennel-Matern paper, the modeled zooplankton also it takes a very steep decline right before the bloom. So that is something both papers had in common. And I should also mention zooplankton is not something you can measure with satellites. Chlorophyll is about the only thing you could use to compare your model phytoplankton with, but with zooplankton, you can only do that in situ, like using a net off the side of the boat, and that's only like that doesn't tell you anything of what's happening 1,000 feet further out in the ocean. Okay, so it's getting near 4 o'clock, so I am going to go ahead and skip ahead to our conclusions here. So what's the story we tell with our model? Well, we're saying that when sunlight increases and turbulence decreases, a system with a low zooplankton concentration is going to be temporarily attracted towards a phytoplankton-only equilibrium before returning to a balanced coexisting state. So that is the story we're telling of what happens during a bloom. And our results agree with Barenfeld and Voss' idea that I mentioned earlier, that marine phytoplankton blooms will result from disruption in the balance of the predator-prey relationship. In other words, it's ecological. So some future considerations we could do, like the Kuhn-Fennel, maybe make things just a little bit more realistic. See what happens. See if incorporating sea temperature in the model and investigating its effects on bloom dynamics, or perhaps trying a non-closed system by allowing nutrients to enter or exit the system, because that happens over the course of the year, and also perhaps improve our numerical scheme. Our system is conservative, but nitrogen I've noticed nitrogen is not conserved well when our Dmax or mixed layer diffusion is higher than 10 to the negative third meters per second squared. Okay, before I close, I'll just mention our references. These two are the papers that we got out of the study, and of course here's some other papers I mentioned in the talk. And here are our two sources of data. The first one was for where we got the chlorophyll and the solar radiation, and the second one was where we got the data for the mixed layer depth. And with that, I will go ahead and open the floor to questions.
Okay. Great, thank you, Seth. That was a really interesting talk and really cool to see some of those dynamics at play. Did anybody have any questions for Seth?
I have a few questions.
Sure.
So, I mean, thank you for the great talk. So if you go back to slide 13. Okay, so I mean, you're linearizing I mean, if you my understanding is you're trying to linearize about a steady state. So when you say equilibria, you mean you're trying to find the steady states of the system, yes?
Okay.
Okay. So I'm just trying to understand the notion of stability that you're using here, if you don't mind elaborating further. So then once you have steady states, you have to first compute them.
Yeah.
Then you linearize about them, right?
Mm-hmm.
Then you set your eigenvalue problem.
Yep.
Okay. So then it's a task to figure out the stability.
Yep.
So I'm just trying to understand your methodology, like a little bit better. I mean, if it's okay.
Okay. All right. Let's see.
So if you could go to slide 16, for example, and look at the yes. I mean, so the y-axis is what again?
Okay, that is technically that's the common log of Dmax. That is the mixed layer diffusion level. So that's in oceanographers. They always say 10 to the minus something. So I just give you the exponent. So you think of that as just the amount of diffusion in the mixed layer where the plankton are.
So the bifurcation diagram is showing that the stability of your steady states or stability of something else.
Of the steady states, yes. Matter of fact, let's see. I should say white region is where the only one that exists is the plankton free one, and it's stable. And in the aqua region, phytoplankton only and plankton free, they both exist, but only the phytoplankton one is stable. And in the yellow, all three exist, but only the coexisting equilibrium is stable.
I see.
Yeah. So basically, this is I go through and I do these computations for all three of them, for all three of those states, and then in this diagram, it just shows, just takes that largest eigenvalue, and it's either positive or negative, and it draws out the boundaries.
Okay. So you're looking at like a principal eigenvalue problem here. So another question that I have is, do you have any boundary conditions for your PDE?
Yeah, no flux at the surface and at the bottom.
I see. And then your 3D systems in the ODE, it is dimensionless, correct?
Let's see. No, it is not, but I do. Let's see. Okay. You said the ODEs.
Yeah.
I do. Let's see. It is not. I don't believe.
It is not dimensionless.
No.
Okay. I mean, so when you plot them, so that means your axes have units.
Mm-hmm.
Okay. I mean, I don't want to ask all the questions, so I'll let somebody else if they have questions.
Caitlin, did you have a question or?
Oh, I was just going to comment. I generally like your questions, Emmanuel. Keep asking them, please. I find I often learn a lot when you your questions as well.
Well, I mean, I have a few other questions then. So in your plot, if you go back to your ODE plot, right, where you had the saddle, the phase space. Yep.
Okay, hold on. You mean this one?
Yeah.
Oh.
So 0 is a phase, 0 is a saddle, right?
Okay, down here.
Yeah.
Yes, that's
The
the
extension state. 0, 0. The orange.
Oh, 0, 0. Let's see. Don't remember that one.
I mean, if you look at the phase portrait,
it's been a while. I don't in this case I remember, let's see.
there's P bar is stable.
Okay. If you're looking at this one right here, P bar is a saddle. It's not. It's unstable because it's a saddle.
Yeah. So then you have this arrow going up to this thing, right?
Mm-hmm.
So then the direction going inside P bar is a stable direction, yes?
The direction going inside P bar. What do you mean the direct?
On the P axis.
On the P axis. Okay, so okay, stable manifold is the P axis.
Okay. So do you have an unstable manifold on the Z axis?
As in for 0, 0. Is that
Yes.
what you're asking?
Yes.
Okay. Be honest, it's been a while. I don't remember what the state for the origin was in this one.
Okay. May I ask one last question?
Sure.
So when you're computing the steady state solutions,
Mm-hmm.
so for me, I mean, if you go back all the way at the end,
The end of what?
where you had those those steady state solutions computed, it looked like
Right here.
yes.
Mm-hmm.
So it's interesting to me because I mean, usually, right, you have either pulses or fronts as solutions of those reaction diffusion equations.
Mm-hmm.
But here it seems like you have, I mean, the plot seems inverted and you only plotted half, but I think it's for realistic purposes, correct?
Okay. Inverted.
So usually you have the spatial dimension on the x-axis and y is something else, right? So yeah. So any intuition on the orientation?
I did this for let's see, just to show well okay, he's for kind of I guess for perspective, since this is depth in the ocean, thought it was easier to think of them that way. Because depth is down, because this is the surface surface of the ocean is 0, and there's 50 feet down, 100 feet down, 150 feet down, and so forth.
Okay. Yeah, I mean, yeah, that's all I got. So I appreciate it. Yep.
Excuse me.
I just had one quick question, if that's okay.
Sure.
For the plot you showed where the phytoplankton population was just out of phase with the chlorophyll measurement.
Yep.
Do you have a suspicion as to what's causing it to be out of phase, or maybe the chlorophyll just becomes detectable, like lagged after the bloom, or is it just maybe a parameter you think that, like maybe it's nutrient upwelling causes it to take a little longer to actually happen, or?
Okay, I think the last thing you said is what was is something I suspect. That's part of the reason I wanted to check that out in future work. And also I skipped over this slide just for time's sake. This is at least this shows in a different oh gosh, somehow I have to explain here, but at least it seems like if you just look at the Dmax versus rho trajectory, which is just this dashed curve here, and right here this star right here is the winter solstice, and you see what happens is it just turns away. It turns away from that region of the phytoplankton only stability, like right away after the winter solstice, and that would explain in the winter solstice right here in the sunlight, and see how that happens every time with the blooms. So I'm suspecting, let's see, like things like maybe sea surface temperature that would affect the phytoplankton growth term, and that would be in the growth term, multiplied by rho, or maybe incorporated in rho. So that would change stuff that's going on here, maybe change this curve a little bit. So that's what I suspect.
I see. Okay. Cool. Okay. Yeah. Interesting. Okay. I guess, yeah, unless there's any other questions, we can thank Seth for an interesting talk. I'll click the little clap emoji, and yeah. Okay. And then we'll, of course, post this on YouTube for anybody that had to miss it. And I believe next week we do not have a talk because it's Memorial Day, but we'll pick up the week after that.
Okay.
Thanks, everyone.
All right.